G'day everyone, welcome to lecture 4 of topic 1 of unit 3, specific heat capacity. We're going to go back. This video will be covering the main ideas of chapter 2.2 of book 1. You should complete this reading before class. So, here are the learning intentions and success criteria for this chapter. Please pause the video and complete the KS table down the bottom right corner there. Okay, so having looked through here, we can see a few knowledge skills. There is an knowledge verbs, and there is a skill verb there as well. We need to know, well, what is Kelvin scale? If we're going to do any calculations with it, we definitely need to know what it is. We need to know what is specific heat capacity, and we need to know what is calorimetry. And finally, for skills, we need to know, well, how do I calculate a Kelvin temperature? Okay. Let's get into it. So for units, in your class readings you went over chapter 1.5 where the text talks about different units used for measuring temperature. Now to summarize this briefly, there is Fahrenheit, we'll never use it, pretend it doesn't exist. Celsius is very commonly used and the text will often give you numbers in Celsius, but some formulas can't use Celsius, so you've got to be careful of that. Kelvin, not all that common in our day-to-day lives, and not often, values aren't often written in Kelvin in textbooks unless they have to at high school levels. But all formulas will work with Kelvin. There's no formulas that only work with Celsius, they will all work with Kelvin. Now, how do we convert between the two? We can convert Celsius to Kelvin by adding 273. So that's what I've written here at the top. K, Kelvin, equals Celsius, plus 273. The way it's written in your formula booklet looks like this. T subscript K equals T subscript C plus 273. So if you forget what the conversion factor is, it's there in the formula booklet. You'll have that for both the data test and the final year exam. But you need to remember, okay, you need to remember that you must use Kelvin for certain formulas, and others you can get away with it. So which ones can we get away with it? When do we use Kelvin? When do we use Celsius? Well, here's the good news. If you're not certain, turn it to Kelvin. Kelvin will always work. There are no formulas there in the formula booklet that Kelvin will not work. If you have a difference in temperature, like our Q equals MCAT formula, under specific heat capacity, oops, thought I had it there. I'll write it instead. So if you have a formula like this, Q equals MC delta T, this here, this delta, if you have a difference in Celsius is the same thing as a difference in Kelvin, because the two things are just shifted by 273. Fahrenheit, it doesn't work, because Fahrenheit to Kelvin you've got to go through a 9/5 conversion factor or some junk like that. So if it has a difference in temperature, you can use Celsius. If you have just temperature though, you have to use Kelvin. Wien's law in unit 4 only uses temperature, not difference in temperature. So that's one that you can't use the Celsius value, you've got to use the Kelvin value. But those are the only two formulas, so Wien's law and this one here. So for unit 3, you're okay with either. Unit 4, you've got to use Kelvin when we do our quantum mechanics down the track. Okay. There are some you may look up for your student experiments. If you do a student experiment on temperature, that you might need to double check what you've got to use it for. Okay, so let's talk about specific heat capacity. In video 2, I talked about factors that influence how fast a kettle of water can boil, and we identified a constant there at the end called specific heat capacity. This is a property of material that tells you how much energy it takes to raise a 1 kilogram mass by 1 Kelvin, or 1 Celsius, because changing by Kelvin is the same as changing by 1 Celsius. Okay, so specific heat capacity, how much energy it takes to make 1 kilogram of that stuff go up 1 degree. That's it. Okay. One really sucky thing to take note is that some websites will give you these in joules per kilogram Kelvin, what we've got here. Sometimes they'll give it to you in joules per gram Kelvin. There are even some that will give you it in kilojoules per kilogram Kelvin, but they're not as common. Okay. You've got to be careful with that. Right? And the websites differ depending on if they're dealing with small things or large things. Now, the default one, the three that we give you in the formula booklet for water, ice and steam, pardon me, are all in this one, joules per kilogram Kelvin. Anything else on the final exam, I would expect them to be given in that same standard unit, but if you read what the unit actually means, it's pretty easy to swap. So let's start with this. Joules per gram Kelvin means for every gram you want to raise a Kelvin, you need this many joules. While joules per kilogram Kelvin means for every kilogram you want to raise a Kelvin, you need this many joules. Okay. Since a kilogram is 1,000 grams, to go from joules per gram Kelvin to joules per kilogram Kelvin, you just multiply by 1,000. Because this is telling you, for one gram, you're going to give this much energy. For 1,000 grams, you're going to give this much energy. So to turn this to this, we multiply by 1,000. I can't expect you to need this, at least in your final exam, but it may be worthwhile just sort of wrapping your head around, especially if you're doing any research on heat stuff for your experiment, just in case, because it would be really sucky for you to say, oh yeah, water has a 4.2 specific heat capacity, while aluminium is over 100, so we'd expect aluminium to take longer, but it didn't, so obviously the science is wrong when you've got the wrong units. Let's have a look at some examples of this. So, this is example 2.2a from the text. It is a little bit blurry. I'm not sure why my camera is doing that, but you should be able to see most of the key points. At worst, load up the textbook and have a look at it while I'm doing it. There are worked examples. The textbook does have worked examples for all these. However, I'll go through how I like to do them and set them out in my thinking as well. So, first part of it, how much thermal energy is required to heat the following items from 30 degrees Celsius to 120 degrees Celsius. We've got a 2 kilogram barbecue plate made out of steel, and second one, $2 coin of mass 6.6 grams, given the specific heat capacity of this. Okay, so let's have a look at these things. In the question, we're asking, well, what is Q? So let's start off. We need to know what is Q. That's thermal energy. We're after Q. Write it down. Always write it down. We need a temperature change. We're going from 30 to 120. Delta T. Now, a change, it means final, take away, initial. Now, you can probably do some of these in your head, but if you can't set it out, final change means final, take, initial. Final is 120, initial is 30. It's going up by 90 degrees. Okay, now we need, we've got a mass there, 2 kilograms. M equals 2.0, because they're given two digits. And we're told it's made out of steel. So C. Okay, now for this, we need to go to the text. There is a table of these on page 92, which is where this worked example actually is. You can see a big list of different things there. Sometimes you might just have to go, well, I think this is about the right one, by having a look at the different things. But here after steel, iron and steel, 460. And if you look at the heading, it says joules per kilogram per Kelvin for the specific heat capacity. So we need to make sure we get that right unit. In fact, I'm going to write this here. We can put this as, hang on, I won't do slash because that's weird, the eraser doesn't work. Because a difference in centigrade is also a difference in Kelvin. So this was 460 joules per kilogram Kelvin. So the formula is Q equals mc delta T. I call this Q equals mcat because the delta kind of looks like an A, and so then it's Q equals mcat. But let's have a look at the units. 2 kilograms. This is in joules per kilogram, so that's good. We've got the right specific heat capacity for the kilograms. This is in centigrade or Kelvin. That's in Kelvin, so that's okay. These things all match up. Now we just need to substitute and solve. M equals 2, C equals 460, difference in T equals 90. Plug that into a calculator. We're going to get 82,800 joules. Now, how much of that are we confident about? We need to think about our significant figures here. We're told that there's 30, that's got 2 significant figures. 120 has 3, but 2 is our smallest. 2.0 has 2. This has 3, so we need to turn this to, round it to 3 significant figures, joules for energy, because this needs to be rounded off. Okay. Now, on your data test, you'll get told what significant figures to write things to. Same for your final exam from the examples we've seen. Your student experiment, I won't tell you what significant figures you have to do. You're going to have to figure that out. That's part of the learning process. Okay. So do be careful with that. Let's have a look at B. We now have still have the same delta T. We have a different C here. We've been told C equals 380 joules per kilogram Kelvin. Now, when you're doing your working out on an exam, for example, if you don't write the units, I'm not going to lose marks for that. I'm just doing that so I can show you how we can double check these things as we're practicing. Mass, though, equals 6.6 grams. We need to turn that into kilograms. To turn a gram into a kilogram, we need to divide by 1,000. I'm just going to leave it like that for the moment because it's easier than doing the conversion and then writing out a whole bunch of decimal points. I'm going to use the same formula. Q equals mc delta T, 6.6 over 1,000 times 380 times 90 gives us a final answer of 226 or 230 with significant figures. Okay, that easy. We just need to plug the right numbers in and we're good to go. Okay, so look at the next one. How much heat energy is required to bring a saucepan containing 500 ml of water at 20 degrees Celsius to boiling point? And we're told here 1 litre of water has a mass of 1 kilogram. Okay, so the good thing is whenever you're dealing with water, often you'll be given volumes in milliliters or litres of water. You will need to convert it to a mass, but the conversion's pretty easy. 1 litre is 1 kilogram, so 500 ml is half a litre, so it's half a kilogram. So we have mass equals 0.5 kilograms. Here's a little bit of contextual knowledge though. What's the boiling point of water? You're not told this. Delta T equals Tf minus Ti. Sometimes, and there will be questions like that where for water especially, you're expected to know what the boiling and freezing point is because you've seen it in every class since probably grade 2, grade 3 in primary school. If it's something like, what's the melting point of iron, they will tell you what that is. They're not going to ask you to memorize a whole bunch of different materials. But water, you're expected to know. The boiling point is 100, and we're starting at 20 equals 80. And finally, the specific heat capacity. Again, we go back to our table. Liquid water has a specific heat capacity of 4,180 joules per kilogram Kelvin, and if you have had a look at that table, you'll see that water is the highest by far on that table. It has a very, very high specific heat capacity, which is probably has something to do with why it's so important for biology. And again, we're trying to work out heat energy, so Q, chuck it in the formula, Q equals mc delta T equals 0.5 times 80 times 4180, which is just the same as 40 times 4180, which is going to be, plug it into a calculator because it'll be a big number, 1.67 times 10 to the 5 joules. So let's have a look at our numbers we were given here. This has 3 or 4 significant figures, depending on how you read it. This only has 2, and that became because 20 only had 2. This had 3 because it was 500 milliliters, and we've just converted it into a different unit. So this minimum is 2, so that means 1.7 times 10 to the 5 joules. That easy. Alright. The last thing I'll talk about, and we'll be doing work with this in video 1.6, but I wanted to talk about where this is going to go. Let's imagine that I have 2 identical cubes. Same material, same size. One is 20 degrees, one is 80 degrees, and I put them next to each other like I have up here in the picture. What happens to the temperature? Well, obviously, 20 warms up and the 80 cools down. There would be some issues with the room, but we're going to pretend that doesn't exist for most of high school science. We like to make things as nice and simple as possible because it's already hard enough. What's the final temperature going to be? Now, I've kind of given you the answer there. It would probably be about 50 degrees. It's halfway between the two values. If the cold cube gets hotter, the hot cube gets colder. Yes, I think I said that right. Because the energy from one moves into the energy of the other. They want to be the same temperature, and so the energy moves to make that possible. But what would happen if the mass was different? What would happen if the materials were different? What if instead of, say, copper and copper, we had copper and iron? Would it still meet at 50 degrees? What if we had a 2 kilogram block of copper and a 1 kilogram block of copper? Where would the temperature be? Now we can use this Q equal mc delta T formula to find that final temperature, and this is called calorimetry. And as I said, that'll be a topic of a later video. And we can also use it for working out how much something weighs, or the actual specific heat capacity of it, by using this technique, and that is going to be one of our mandatory pracs that we're going to do a little bit later on. Okay, I just for now wanted to sort of mention where this is going, and if you're doing chemistry, you'll probably get there a little bit faster than we will, but you'll be doing the same topic. Mrs. Gantemov will present it slightly differently, but it's the same core theory. So, in this video we have gone over the following. We have explained situations that require the use of the Kelvin scale. We've defined specific heat capacity and started using it in equations. And we've described the technique of calorimetry. For your entrance to class, please complete questions 1 to 4 in chapter 2.2, and then copy your answers into the 3.1.4 space on eLearn. Thanks very much for listening, guys. Have a great day.